Okay, this is video number 2 for chapter 5. In this video, and then the last one, the third one, we're going to be doing just a bunch of example problems. So let's get started. So we're going to start with the example problem here on the left-hand side. It's looking at the heat transfer through 1 square foot of a wall made up of 5/8 inch thick gypsum board, as well as 5/8 inch thick Douglas sphere plywood. And it's saying that the wall temperature difference, so from the outside to the inside surface of the wall, there's a 10-degree difference in temperature. So what we're going to do first is get the thermal resistances of of each of those materials. So again, these will be table 5.1a. So if we look at table 5.1a, you'll be able to find gypsum. So in the particular case of this example problem, as I go back and look at the table, you can find gypsum towards the top of page 122. Now you can see that gypsum on the top of page 122 has two thicknesses. You have one that's at 3/8 inch and another one at 1/2 inch. Since 1/2 inch is the closest in thickness to 5/8, what we're going to do is that we're going to take the thermal property it gives us, which is the conductance. It gives it to us as 2.22 BTU per hour foot squared Fahrenheit. And what we're going to do is that we're going to set that equal to 1 over the resistance, or K over delta X. And knowing that the thickness, the tabulated thickness, is 1/2 inch, we can go ahead and extract what the thermal conductivity is. And again, that's BTU inch per hour foot squared Fahrenheit. And knowing that resistance is thickness over conductivity, and our thickness is 0.625, we can divide that by the thermal conductivity that we just calculated, and we can get that the resistance for our gypsum board is 0.563, and again that would be hour foot squared Fahrenheit per BTU. Okay, so next we're going to look at the plywood. So if we look at Douglas sphere plywood, again, it's still table 5.1. The thing to do is to find where on the table it is. So it's right under gypsum. You can see that it has a lot of different thicknesses. For plywood, it has 1/4 inch, 3/8, 1/2, and 3/4. Ours is 5/8 inch thick. So I'm going to go to the 1, 2, 3, 4th entry on the table on page 122, and you can see that it doesn't give for a thickness, but it does give us conductivity for the entry without a thickness. It gives a conductivity of 0.8. I'm going to leave out the units so it's not to take up as much room on the slide. So in that case, we can compute the resistance, right, as thickness over conductivity. Our thickness is 0.625 inches divided by conductivity, which is 0.8, gives us a resistance of 0.781 BTU, hour foot squared Fahrenheit per BTU. So if we do that, I'm going to continue the example problem here. Our total resistance will equal the resistance of the gypsum plus the resistance of the plywood, giving us a total resistance of 1.34 hour foot squared Fahrenheit per BTU. I'm going to introduce a concept called overall heat transfer coefficient. It's equal to 1 over the resistance, where Q can equal UA delta T. So if U is 1 over the resistance times the area, which it gives us per square foot, times 10 degrees difference, it gives us that our heat flux is going to be 7.4 BTU per hour per foot squared, right? So again, what's interesting about this particular problem is that it's looking at the heat transfer through the two boards in series where you have the temperature on each side of the wall. Now, what we're going to do is do the same problem, but instead of the temperature difference being on each side of the wall, it's going to be the temperature difference is 10 degrees between the inside air and the outside air. And the difference is here is that we have to take convection into account. So if we go to table 5.2a on page, excuse me for a minute while I turn to it. This is on page 131, assuming this to be a dark surface, right, emittance of 0.9, you can get that the resistance for is a vertical wall, position of the surface is a vertical wall and still air with horizontal heat flow. You'll find that the resistance, thermal resistance for convection on each side of the wall, if the air is still, is 0.68 hour foot squared Fahrenheit per BTU. So with that said, our total resistance is going to be the indoor convection plus the resistance for the gypsum, plywood, and the inside convection for still air. So now we get a total resistance of 2.7, and again, that's BTU per hour foot squared. I'm sorry, hour foot squared Fahrenheit per BTU. Our overall heat transfer coefficient is going to be 1 over the sum of all that resistance. So it's going to be, well, just to make that a little simpler, it's 1 over the total resistance. So if we go ahead and we add up our Q now, where it's U times A times delta T, 10 degrees. In this case, we get 3.7 BTU per hour per foot squared. So the heat transfer, just counting it between the two surfaces of the wall, was 7.4 BTU per hour per foot squared. And yet it's 3.7 if we take into account the convection on each side of the wall. So that's just to say the convection has a huge impact on our overall heat transfer. All right. So let's go on to a second example problem here. So this problem is saying compute the overall thermal resistance of a wall made up of 100 millimeter face brick and 100 millimeter common brick. I'll give you the densities for each of those bricks with a 20 millimeter air gap. There's 13 millimeters of gypsum plaster and 12.7 millimeters of plywood on the inside. Assume a 7 meter per second velocity on the outside and still air inside. And assume the outside temperature to be 2C and the inside temperature to be 22C. So with this problem is what we're doing is that we're just basically trying to find the overall thermal resistance of this wall. And the best way to do this is to tabulate our values. Here's what I mean. I'm going to go ahead and make a table, right, taking into account the properties that we look up from the tables in the book, and using this as a method to kind of bring together and to tabulate the thermal properties of the materials relative to what I need. So I'm going to do temperature, I'm sorry, not temperature, thickness, conductivity. I'll go ahead and put thickness as delta X. Conductivity, resistance, density in case we need it. And just to make sure that we're all on the same page, I'll go ahead and just put table number just to make sure we know where to get it. What I'm going to do here is just put out the composition of the wall, starting with outside air. Looks like the next material is face brick, followed by an air gap, followed by common brick, then plywood, gypsum, and then inside air. All right, so we finish off the table here. And what we're going to do is go to each of the tables and then pull out the values that we need. What I'll challenge you to do is to follow along as best you can with me and to go and look up these values for yourself. So if you're to do this, oh, and then on the bottom, sorry, the bottom of the chart, what we'll do, so we'll have the total resistance and just, sorry, excuse me. What we'll do is just go ahead and total it up. All right, so starting with outside air. Outside air, it looks like we're looking at, again, this is table 5.2. We have outside air traveling at 7 meters per second. So it looks like the closest to that was that outside air would be for the winter time. We have 7 meters per 6.7 meters per second for the winter. So if we were to pull out our thermal resistance for the outside air, we would get a thermal resistance in SI units of 0.029, that's meters squared Celsius per watt. Again, that would be on page 131 for table 5.2a. So moving on to the next one, looking at face brick. So face brick, as I turn through this book, let's look through the table until you find them. What we need are SI units. So you would start at page 125. And again, this would be table 5.1b. It looks like face brick. Face brick would be, okay, so if you look at the middle of page 127, right under masonry materials, you see two different types of brick, right? So here it's telling us that face brick has a density of 1920 kilograms per meters cubed, and common brick has 2080. So if you look at that, it gives you a conductivity range. So if you look, for example, for face brick, the density at 1920 kilograms per meters cubed, it gives you a conductivity range between 0.81 and 0.98 watts per meter Celsius. So with that being the case, what we would do is take the average. So if you take the average between these two conductivity values, you would end up with about a conductivity of 0.895. The resistance of that would be the thickness you have over the conductivity. The thickness of the face brick is 100 millimeters, right? So if you plug in these values of 100 millimeters for the thickness, and then you have the conductivity of 0.85, and you do your right unit conversion, you should end up, again, the conductivity is about 0.895, the thickness is 0.1. You divide this into 0.1, and you should get a resistance of 0.112, and that would be meters squared Celsius per watt. All right. Now we will do the same thing for common brick. Now the only difference between common brick and face brick is they're both brick, they're just different densities. So again, if you look up the density for a common brick at 2080 kilograms per meter cubed, you have a conductivity range between 0.92 and 1.12, which gives you an average of 1.02. You have a thickness of 0.1. If you do the math, you should get a conductivity or a resistance of 0.098. Okay, next we have the plywood. If you look at the plywood, we're given that the plywood thickness is 12.7 millimeters, right? 12.7 millimeters. So if you have a thickness of 12.7 millimeters, I'm going to go back and I'm going to try to find plywood at that thickness. So if you look on page 125 towards the bottom, and again, this is all table 5.1b, bottom of the page. The start of 5.1b, you would have this as 1, 2, 3, 4, 5, 6, the seventh entry, plywood, Douglas fir plywood, gives you a conductance of 9.1 watt per meter squared Celsius. And the resistance is just simply 1 over that. So I come back, get my resistance here, 0.110. Next entry is gypsum. Again, table 5.1b. The top, and then this gypsum has a 13 millimeter thickness. But if you go back to the table, you don't really have 13 millimeters of thickness. But what I do have is it gives you the basically gypsum, excuse me, it gives you gypsum at a thickness of 12.7 or 12.5. So if you look at gypsum at 12.7 millimeters, the conductance is 12.6 watts per meter squared Celsius. Now, again, conductance would be conductivity over thickness. So that would be 12.6 equals K over 12.7, or not really 12.7, sorry, it would be 0.0127 since it's going to be in meters. So we can go ahead. I know, guys, this is really slow, but I'm hoping this me going slow here will help. So again, 0.127, we take that, 0.0127, we multiply it by 12.6, we get a conductivity of 0.16, it's watts per meter Kelvin, or meter, not meter Kelvin, but meter Celsius. And then we get the resistance is the thickness over conductivity. So we would have 13.013 meters divided by the conductivity, which is 0.16. So if I do that, I end up with gypsum having a resistance of 0.081 And then finally, inside air, if you were to go ahead to the table, again, that's table 5.2a. If I go to table 5.2a and I want to look up for still air on the inside for a vertical surface, horizontal heat transfer for emissivity of 0.9, assuming dark surfaces, I would get a resistance of 0.12. So then I'm finished at this point with all my individual values, and then I can go through this and add them all up as I am doing now. Oh wait, I'm sorry, I'm not quite done yet. I just realized, and we still have the air gap to do. The air gap is not a table that we've looked at yet, but we're going to be looking at two tables for that. We're first going to have to go to table 5.2b, and then the air gaps are actually in table 5.3. So if you go ahead and if you take your book and you go to table 5.3, there's table 5.3a that starts on page 133, and it goes through table 5.3b, ending at page 136. This is a little bit different in terms of how to use the table. So if you just kind of follow along with me by looking at your book as I verbalize what you're seeing. The left-hand column is the orientation of the airspace, so whether it's a vertical or horizontal airspace. The next column gives you the direction of the heat flow. So if you look at the direction of the heat flow, in this case, we have a vertical airspace with a horizontal heat flow. So that should put you in the third category down on the table on page, give me a second here, page 135. So that's the start of table 5.3b. And the third line down, you should see for vertical space orientation, a horizontal heat flow. Now, the next two things look at airspace in terms of the mean temperature and the temperature difference. So if you look at this, you have the mean temperature would just be the average temperature in the space, right? So if we go ahead and if we look at 2 degrees C and 22 degrees C, it looks like we're at about 11 degrees C, which is the average temperature across the air gap. So let me go up here. The mean temperature across it is about 11 degrees C. So that would put you in one of the two space, if you look at vertical orientation of the airspace and horizontal heat flow, in terms of mean temperature, which is the third column, you should see there's two different entries there for 10 degrees, right? The second and third row under that vertical airspace and horizontal heat flow. The next is looking at the temperature difference. And the delta T across it's about 20 degrees, right? Take 2 minus, or 22 minus 2, you got 20 degrees. So in terms of the fourth column where it looks at temperature difference, the closest to that is going to be 16.7 degrees. So if you look at in the table, a mean temperature difference of 10 degrees and a temperature difference of 16.7. And then we have to look at the thickness of the airspace. So it's telling us that there's a 20 millimeter airspace gap. So if you go back to the table, you'll look that you have numbers for 13 millimeter airspace or 20 millimeter airspace. So we're going to go to the 20 millimeter airspace. Then the last thing is looking at our emittance. All right, so if you look at the average emittance, if you look at this airspace, it's encapsulated between two brick. And brick you can consider a dark surface, so you could probably think of the effective emissivity, which is what those last set of numbers are that you look at the table. If you look at the top of the table, it starts at 0.03, 0.05, 0.2, 0.5, and 0.82. That's the effective emissivity between the two surfaces that encapsulates the airspace. And in that case, it would be about 0.82 would be the highest emissivity value, resembling a dark surface, which is what a brick would be. And so you should end up with 0.17 as the air gap thermal resistance. I know that was a lot to go through. If you have questions on that, obviously ask me, or when I get back, I'll spend some more time going over this. But if I go ahead now and I take all of those resistance values and I add them up, I should end up with a total thermal resistance of 0.72 as my total thermal resistance for this problem set. All right. Okay, I hope that helps. We have a few more example problems to work through, which we'll do in the third video, but that'll be it for this one. Thank you.